The main aim of this work is to design deep learning models to detect slippage while concurrently identifying texture of a grasped object and speed of motion. As input, we used high-bandwidth accelerometer readings. In order to collect data related to these classification and regression tasks, we built an experimental platform. The setup consists of a motor, a gripper with fingertips, encoders to measure velocity of motion, and a custom-made data acquisition system to record vibrations generated by friction using accelerometers. We defined 3 types of motion: slippage, sliding, and no motion. Slippage occurs when the grasped object moves with respect to the gripper. Sliding takes place when an external object traverses on the grasped object. Finally, no motion happens when neither slippage nor sliding exists. The collected dataset contains 6 channels of accelerometer readings. During training, we used 8 combinations of the accelerometer readings to identify how each combination affects the performance. We utilized 3 different deep learning architectures such as FNN, LSTM, and CNN. We used AlexNet architecture as our CNN model. We tuned hyperparameters using validation dataset. Finally, we trained the model successfully and obtained 95% accuracy for the motion detection task. For texture detection, the highest accuracy was 96%. Finally, we obtained 3.4 cm per second standard deviation for the speed detection. We also computed delay in detecting slippage. It was equal to 17 milliseconds for CNN model. In addition, bandwidth higher than 125 Hz is suitable to achieve more than 80% accuracy in the motion detection task.
Handover, which can be described as a sequence of coordinated join actions aimed at directly transferring an object from a passer to a receiver, is a fundamental tool for any cooperation activity. People perform this process the uncountable number of times. However, replacing the receiver with a robot is a challenging task. The ability to pass or receive soft objects is still an unsolved task. A wide range of sensory inputs allow humans to distinguish deformable and fragile objects from rigid ones. Accordingly, humans adapt their grasping force to avoid damage and at the same time slippage. Excessive grasping force may damage soft or delicate objects in the handover process. Therefore, our idea is to set the upper bound of grasping force in order to prevent undesirable deformation of soft objects. But if we use this upper bound for every object, including rigid ones, then the object may slip because of insufficient force. We use 2 limits for soft and rigid objects. Thus, to know which one of the limits to use, we introduce a prior-to-pass classification of soft and rigid objects. The classification is done via TactileLab, which was designed and constructed in our lab. This glove consists of different sensing modalities: pressure and vibration. The former is implemented with arrays of barometers molded within silicon, while the latter with 2 MEMS accelerometers. We've invited several people to collect the data to train our neural network. Subjects were asked to grasp soft and rigid objects while wearing tactile glove. As a result, based on this dataset, we could achieve 97% accuracy of classification with CNN model. In our novel proposed handover, the role of receiver is performed by Franca Amica robot, integrated with Allegra hand. The role of passer is a human being, wearing a tactile glove. The participant grasps an object and an algorithm classifies if it's soft or rigid. Then, the camera tracks the position of the human hand, and robot moves to this position. After that, the participant places the object into the robot hand. This contact is detected via spike and robot arm torques. After that, the robot grasps an object and places it in the corresponding box. In addition to classification, tactile glove also gives us ability to detect when the person released an object. This is used in order to assure safety of object and comfortable handover, because the robot should not retreat until the person releases the object. In addition to the objects used in the dataset collection, we added 6 more to test our classification on unseen objects. Furthermore, we tested our approach on 4 people who helped with dataset collection and 4 new people.
Vibra is a vibro-tactile tool connected with a head-mounted display to provide haptic feedback that can generate illusions of squeezing objects with various stiffness coefficients. Before going further, let's shed a light on the theory behind the haptic illusions. Vibrations are undoubtedly important to us as we discriminate different surface textures, detect a slip of a grasped object, and even infer a limb displacement, all due to being able to sense the vibrations that occur at the contact points. There are 4 primary tactile mechanoreceptors: Merkel's disc, Ruffini endings, Meissner's corpuscles, and Pachinian corpuscles. The last detect transient pressure and high-frequency vibration. Detected vibrotactile stimuli go through the nerve and cause haptic illusions. This trick is widely implemented on the latest smartphones, video game controllers, car interior interfaces, and wearable electronics. In other words, everywhere where we need to give a sense of touch as actions as tapping, pressing, rotating, and sliding over various textures. So in our case, haptic illusions is reached with Vibra and Oculus Rift goggles. The enclosing structure of our device was 3D printed from liquid polymer resin. The haptic system consists of two main parts, a force-sensitive resistor and a voice coil actuator. The FSRs measure the applied normal force. This force modulates the oscillating frequency of the voice coil actuator. Two springs isolate vibrations and ensure that the most amount of vibrations propagate to the user's fingertips through the side parts. With Vibro, we can imitate actions like a squeeze of a soft granular object, for example a rubber sack filled with a granular particles such as coffee grains. In addition to the device itself, we created an environment in VR using the Unity game engine. Through HMD, a user can see a virtual hand model and a virtual soft object. The object consists of a set of tiny particles connected to each other as in real-world physics. The deformation of the soft object is modeled in real time with the use of force values obtained by FSR. A combination of the hardware and VR parameters give us 18 working modes that differ by vibration frequency level, the range of applied force, and VR animation speed. Experiments with 10 tests show that amplification is usually larger at lower oscillation frequencies. Also, a larger limb displacement is sensed for higher force threshold values. To sum up, it has been revealed that varying the ratio between the rate of change of the motor frequency and the rate of change of the shape of the soft object seen in HMD renders stiffness parameters of the soft object to the rigid handheld controller.